We obtain a series combination of resistors by joining one of the two endpoints of a resistor to the next resistor. We can make a series combination using 2, 3, and so on up to n resistors. In order to obtain the parallel combination of resistors, we join one end of all the resistors and similarly join the other end of all the resistors. A parallel combination can be made using any number of resistors. Also, a mixed combination of resistors is obtained by connecting some resistors in series and some resistors in parallel combination and then connecting the two combinations. So far, we have seen how to build various types of combinations of resistors. Next, we will learn about equivalent resistance of any combination of resistors in a circuit. Equivalent resistance is the resistance of a single resistor that can replace the given combination of resistors in the circuit without affecting the total current in the combination and the voltage across the combination. Let us now derive equations to find the equivalent resistance of the various types of combinations of resistors. Equivalent resistance of a series combination is obtained as follows. PQ and RS are two resistors with resistances R1 and R2 joined in series as shown in the circuit diagram. A voltage V is applied across points E and S by joining them to the two terminals of a battery. V is the potential difference between points P and S. The charge that leaves R1 enters R2. As current is the measure of the rate of flow of charge, the seen current I must flow through R1 and R2. According to Ohm's law, V is equal to I into R, where V is the voltage across the resistor, I is the current flowing through the resistor, and R is the resistance of the resistor. Applying Ohm's law to resistor 1, the potential difference across R1 is denoted by the equation V1 is equal to I into R1. Let us label this as equation 1. The potential difference across R2 is denoted by the equation V2 is equal to I into R2. Let us label this as equation 2. The potential difference V across P and S, that is, the series combination, can be written as V is equal to V1 plus V2. Let us label this as equation 3. Substituting equation 1 and 2 in 3, we get V is equal to IR1 plus IR2. V is equal to I into R1 plus R2. Let us label this as equation 4. Equation 4 can be written in the form V is equal to I into R equivalent. Let us label this as equation 5. From equations 4 and 5, we can write R equivalent is equal to R1 plus R2. Let us label this as equation 6. From equation 6, we conclude that when two resistors R1 and R2 are connected in series, the combination has an equivalent resistance equal to R1 plus R2. When three resistors of resistances R1, R2, and R3 are connected in series, The equivalent resistance for this combination is equal to R1 plus R2 plus R3. We can extend this to a series combination of n number of resistors with resistances R1, R2 and so on up to Rn. The equivalent resistance of this combination is equal to R1 plus R2 and so on up to Rn. Now let us consider a parallel combination of resistors AB and CD with resistances R1 and R2 connected as shown to a battery of potential difference of V. The equivalent resistance Req of this parallel combination is obtained as follows. The charge that follows from the source, that is, the battery, splits and flows out partly through R1 and partly through R2. I is the rate of flow from the source. That is, the battery I1 is the current through the resistor R1 and I2 is the current through the resistor R2. We can now write I is equal to I1 plus I2. Let us label this as equation 7. Applying Ohm's law across R1 and R2 individually, we can write V is equal to I1 into R1 and I1 is equal to V by R1. Let us label this as equation 8. Voltage V applied across the two resistors is the same as they are connected parallel to the same battery. Therefore, we can write V is equal to I2 R2 and I2 is equal to V by R2. Let us label this as equation 9. Substituting equations 8 and 9 in equation 7, we get I is equal to V by R1 plus V by R2 and I is equal to V into 1 by R1 plus 1 by R2. Let us label this as equation 10. Equation 10 can be rewritten in the form I is equal to V into 1 by Req. Let us label this as equation 11. Req is the equivalent resistance of the parallel combination of resistors. From equations 10 and 11, we can write 1 by Req is equal to 1 by R1 plus 1 by R2. Let us label this as equation 12. Using equation 12, we can calculate the equivalent resistance Req of the parallel combination of two resistors. Similarly, when there are n resistors connected in the parallel combination, we can write 1 by Req is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. Let us now look at the scenario wherein some resistors are connected in series and some resistors are connected in parallel. The equivalent resistance of such a series and parallel combination is obtained as follows. In the circuit, three resistors of resistances R1, R2, and R3 respectively are connected in a mixed combination. R2 and R3 are in parallel combination. Their equivalent resistance R23EQ is calculated using equation 12. 1 by R23EQ is equal to 1 by R2 plus 1 by R3. Now, R1 and R23EQ form a series combination. Their equivalent resistance, R123EQ, is calculated using equation 6. R123EQ is equal to R23EQ plus R1. It is important to note that we can calculate the equivalent resistance of any combination of resistors using the basic equations 6 and 12.